So we left off talking about different graphical examples of limits, what a limit is, and the next step with that is to talk about continuity. Um, what this means for a graph, what this means for a function. So we say a function is continuous at of point A if the limit as x approaches that value A of the function is equal to the function value at A. And we have a couple of conditions. So the function is continuous if the limit and the function value are the same number, provided that that point that we choose, that value for x we choose, is an element in the domain of f. All that is a fancy way of saying that f of a actually exists, right? I can actually find the function value. The limit exists. So the function value has to exist, the limit has to exist, and of course our definition has to hold true, so the limit and the function value have to be equal. If at any point these are not true, so we'll say if any of these are not true, then we would say that f of x is discontinuous at A. This looks really complicated and convoluted. All this means is, can you draw the function, or well, the function's graph, without picking up your pencil? That's all it means to be continuous. Can I draw the graph without picking up my pencil? If I can do that, then the function is continuous with an asterisk, because we're going to clarify this a little bit. A function is continuous can be continuous in a few different cases. So the first one we'll say is the function is continuous on some open interval if it's continuous at every point in that interval, right? So as long as it's continuous on an interval, and for every value in that interval, we say it's continuous for that interval. If we don't specify any sort of type of continuity, if we just say the function is continuous, that implies that it's continuous everywhere in the domain of f. So I'm going to come back in a minute with what that really implies. If I say the function is continuous everywhere, by everywhere I mean all the real numbers. And of course, if it's not continuous, we say it's discontinuous. So the easiest example that I have of that is to talk about 1 over x. Right, so this is the graph of 1 over x off to the right, and we know that the domain of this function is all real numbers except for 0. So we're going to say that this is a continuous function. And I don't specify any type of continuity, so this just means it's continuous for all x in the domain of f. Right? And that's true, of course, because of the domain. I can look right at it, right? Every x value in the domain is the limit would be equal to the function value, and I can draw this graph within the domain itself without picking up my pen, right? If I were to redraw this without erasing the axis, that would be helpful. If I draw this, right, I'm like this, and then like this, oops, like that. And you're going to say, well, hold on, you did pick up your pen because you had to skip 0. And that's okay because we care about the domain, right? Within the domain itself, I didn't pick up my pencil, so therefore it's continuous on the domain. So it's a continuous function because 0 is not an element of the domain, so we don't need to worry about it anyway. Obviously then it's not continuous if I consider 0 at all. So it's not continuous on any interval, any open interval, containing 0. If I were to consider the open interval -1 to 2, so just to kind of highlight what that means, I'll draw in -1 and I'll draw in 2. If I consider the open interval between those two x values, well, clearly this is not continuous because I have to pick up my pencil at 0. And in this case, because I'm considering 0 as part of my interval, then the function is discontinuous there. So this 0 that we keep coming back to then is called a point of discontinuity. Let's get a point of discontinuity at x equal to 0. So moving on to another example, we want to consider the graph of f of x below, so there it is right there. And I want to determine if the function is continuous at -1, at 0, and at 1. So I want to determine if the function is continuous here at -1, here at 0, and here at 1. Well, let's figure it out. Remember the key thing, we have our 3 big points, and maybe I'll just copy these over so I have them, just for reference. Maybe I'll just we'll shrink them so I have them off to the side, right? So here are my hints, my properties. So I'm going to take this one at a time. First we'll look at x equal to -1. Well, is -1 in the domain? Yes, it is, because I have a function value right there. So x is in the domain of f. Sorry, -1 is in the domain of f. Does the limit exist? So we've established that -1 in the domain of f. Does the limit exist? Let's figure out. From the left, I'm approaching, looks like 2, and from the right, I'm approaching 2. So yeah, the limit exists, that's good. And is it equal to the function value? So if I look at f of -1, right, based on my graph, f of -1 is 2. These are equal. These are equal. So yes, it is continuous. Right, it satisfies all 3 of my qualities. So we can check this for 0 as well. And if you want to try either of these next two on your own, feel free to pause the video and try it for yourself and see what happens. But I'm going to go ahead and continue. So for x equal to 0, well, same thing. There's very clearly a function value right there at 0. So 0 is an element of the domain of f. And the limit as x approaches 0 looks like it's also 0, right? As I approach from the left and from the right, I approach 0 both times. And I'll just move my other problem down here so I have some space. Maybe, possibly. There we go. And then f of 0 is also 0. These match. So f of 0, so x equal to 0 is also continuous. And now we get to x equal to 1. Well, let's see. Is 1 in the domain of f? Yes, it is. The closed circle shows my function value. My function value is 2. Does the limit exist as x approaches 1? Well, let's see. If I go from the left, I'm going this way heading toward 1, and then from the left, the limit is -2. But from the right, the limit is +2, so the limit does not exist. So it doesn't even matter here if it's equal to the function value, because there is no limit. So I don't even need to test the third point, because I know right here, right away, the limit has to exist. Well, it doesn't. So it is discontinuous. We have a point of discontinuity there. So I could state that if I really wanted to. I could say that x equal to -1 is a point of discontinuity. Okay, so now I can look at this from an algebraic perspective with a problem like this. So I've got this piecewise function here, and I want to determine some value of k so that this whole function is actually continuous when x is 1. So as you can see, I've got my properties, my characteristics back down here. A lot of these in these types of problems tend to be more formalities, right? I need to make sure a is in the domain, which in this case it is, right? Because we've stated it in the piecewise function that it's equal to some number k when x is 1. I need the limit to exist, and I need the limit to equal the function value. For these problems, that last piece tends to be the most useful. But as it turns out, step 2 here, or characteristic or property 2 here, is going to help us out a lot as well. So the limit needs to exist. If I were just to go ahead and plug in 1 right now, I don't have a value. If I tried to put it into the cubic function above, in the first part of that piecewise function, it wouldn't exist. I can't divide by 0. But what I can do, and one of the tricks with limits, is if I'm evaluating a limit algebraically, which is what I'm trying to do here, I want to do two things. I want to simplify as much as I can, and then just plug in that number. So let's simplify. If you've noticed here, I've got division. And because it's a linear term that I'm dividing by, I can actually go ahead and use synthetic division to save myself some time. So if I'm dividing by x minus 1, remember I'm going to set up my synthetic division with a 1 on the outside. I have my coefficients listed along the top. That should be a 3, not a 2. And then every time I go step by step, I'm going to multiply up. So 1 times 1 is 1, and then add down, -2. Multiply, add, multiply, add. This works out nice and neat because I got a 0 as a remainder, which is great because this tells me that my scary looking rational function is nothing more than a quadratic function, which of course exists when x is -1, or x is +1. +1 is in the domain of f. That satisfies number 1. Does the limit exist? Well, that's what we're trying to figure out right now. If I simplify, then plug in, I've simplified as far as I can. I'm going to plug in. So if I evaluate this for x equals 1, and that's what this fancy bar notation means, then I'm going to get 1 minus 2 is -1 plus 3 is 2. All right, so we've established then that f of 1 is 2. Sorry, no we have not. We've established that the limit as x approaches 1 is 2. Well, of course, in simplifying this then and plugging in, we've also figured out that f of 1 is 2. And these are equal. So then the value of k that makes this function continuous is 2. Right? If I were to go through and replace this with a 2, then this is going to make my function continuous. So the big takeaway from this is right here. simplify, when you're evaluating a limit algebraically, simplify as much as you can and then plug in. So if we go on to talking about limits at infinity, which I've already kind of hinted at before earlier in the first part, and talking about different types of asymptotes, and we've dealt with this already, right? If I were to take my sticky note, I can draw a grid here so I can draw a graph so we have something to work with. Oops. So if I just go ahead and do this, I come up with some kind of function. Maybe, sure, there's my function. Well, we've talked about asymptotes forever, right? We've talked about it in Algebra 1 and Algebra 2. My vertical asymptote would be right here, right? I have some kind of a line that my graph does not cross because the function is not defined at that point. Well, we're going to kind of amend and update our definition of a vertical asymptote, and we're going to say that some number c is a vertical asymptote, and that's just my way of defining vertical asymptote, or abbreviating it rather, if the limit as x approaches c from the right of the function approaches either positive or negative infinity. So that can be from the left, or it can be from the right. Approaches positive or negative infinity. And that's exactly what you see here. If we call whatever x value this is c, and I go from the left or from the right, if I follow this from the left, I'm approaching positive infinity. If I approach from the right, I'm approaching negative infinity. Then that's kind of our way of now defining a vertical asymptote in terms of limits. It's our way of proving that something's a vertical asymptote. So now it's not just, oh, the function doesn't exist there because I can't divide by 0. It's more than that. It's if I look at the limit at that point, from either direction, I'm approaching one of the infinities. Now, horizontal asymptotes. So again, we've talked about horizontal asymptotes before. If we go back and look at our graph up here, this is my horizontal asymptote right there. Great. How did we define this before? Well, this time we're going to use it the way we did before. We looked at a whole bunch of rules for a horizontal asymptote. We started by talking about my function in terms of its leading coefficient and degree, right? I have two polynomial functions whose degrees are n and d for numerator and denominator, and we had three cases, right? The numerator could be greater than the denominator, in which case there was no horizontal asymptote. The numerator degree could be less than the degree of the denominator, in which case there was a horizontal asymptote at 0. There could be a case where the degrees are equal, in which case the horizontal asymptote was at a y value equal to the ratio of the leading coefficients. These are still crucial, and IB does not cover them, but I'm going to say keep them in your back pocket, use them all the time. I think IB may want to see some sort of limit work here, but these work. They are always true. They are still valid. You should use them. You should still use them. They are still good. But the way that we're going to update this definition, if we wanted to prove that something is a horizontal asymptote, is to say that y equal to k is a horizontal asymptote if the limit as x approaches either positive or negative infinity, depending on the case we're looking at, is that number k. And sure enough, we see that. If we call this y value here k, and I look at my function as I approach positive infinity, I get bigger and bigger and bigger. I get closer and closer and closer to k. Likewise over here, if I get closer and closer to negative infinity, my function value approaches k as well. So I want to sketch here a graph. So one of the things we're going to start talking about a lot in calculus about is curve sketching and graph sketching. So if I want to sketch the graph of x plus 2 over x plus 1 and state the equation of any asymptotes, well, I can. Now, one thing to note is that when IB says sketch, we are still talking about some kind of a rough cut, right? Some kind of a rough, well, sketch, right? It doesn't need to be perfect, but asymptotes, any what we call turning points, be maxima and minima. Maybe I'll just call it that then. And intercepts should be labeled. I did not spell that correctly. Labeled. State the equations of any asymptotes. All right, well, vertical asymptote. We're just going to stick with what we know, right? It ain't broke. We're not going to fix it. It works. There's very obviously a vertical asymptote at -1 because I can't divide by 0. So we're going to go ahead and mark that in. Using our rules, there is a horizontal asymptote at y equals 1, right? The degrees are equal. So we take the ratio of the leading coefficients. The leading coefficients are both 1. So I'm going to go ahead and draw that in also. Now normally I would want to find the equations of any asymptotes. So we're going to need to do that here as well. So, sorry, not asymptotes, intercepts. The equations of any intercepts. So my y-intercepts are where x is equal to 0. So if I do that, then I'm going to get f of 0 equal to 2. So I'm going to plot that. That is an intercept, so because I'm being told to sketch, I need to label that point. And my x-intercepts are where the function's equal to 0. And if I do that, I'm going to get x equal to -2, so I'm going to plot that as well, and it's an intercept, so I'm going to label that also. Now, how do I know which way it's supposed to go? This is where our asymptote definitions come into play. So if I go back up here, we'll start with the horizontal asymptotes here because I think bounding it that way is a little bit easier. Y equal to k is a horizontal asymptote if the limit as you get closer and closer to positive or negative infinity is k. So as I'm approaching plus and minus infinity, my graph should be approaching the horizontal asymptote. So the way that's going to work then is to start here and curve this way. And of course I need to approach the vertical asymptote also, so I'm going to approach that way too. Likewise, my function here needs to approach the horizontal asymptote, and I really can't do it from below because then I wouldn't have a function. So I'm going to go up this way then. I should state the equations of any of my asymptotes, which I have done. I have no maxima or minima to label. I've labeled my intercepts, but I have not labeled my asymptotes, so I should do that here. And there is my sketch. So there's a lot of pieces, a lot of things to keep straight, but if you take it in small chunks, you'll be okay. There's one more thing we need to really consider here. One thing that we haven't talked about before that we need to introduce now is if I look at the function here, it's x squared plus 2x plus 1 divided by x. Now I want to know what I notice about the way this function is bounded. And if you're looking at it, well, we have, I usually do it with the dotted line, but I'll do it with a solid line here just to show it. We have a vertical asymptote just like we normally would. But it also looks like the function doesn't cross a diagonal line, right? There's this diagonal line right about here in green now that the function also doesn't cross. What is this? Can we show this? We can. All right, we notice this kind of curious thing over here, and it's called a slant asymptote. IB uses the word oblique. It's an oblique or slant asymptote. Now, before I do that, before we define what this is, let's see if we can figure out what this line means, or how to express it. If I just look at it, right, it's got a slope of 1, and its y-intercept, if I'm going to 10 here, I'm counting by 2's, right? So this seems to be the line given by the equation y equals x plus 2. Is there another way I can show that? Yeah, of course there is. If I look at my original function, well, I can divide this by x because I have a single term in the denominator. It means I can divide every single term through by x, so I get x plus 2 plus 1 over x. And what do you know? There's that x plus 2 right there. Where's the connection? Well, it looks like there's some kind of a connection between the equation of the slant asymptote and the quotient of my rational function after dividing. That's exactly what this is. So this only happens when the degree of the numerator is equal to 1 more than the degree of the denominator. If I stick with the n and d I used above, that just means n is 1 plus d. These occur at a function, right? That's all that y equal to 2, x plus 2 is, right? And that function is equal to the quotient after dividing numerator by denominator. We don't care about the remainder. We're just going to completely ignore the remainder. Sorry, remainder. We're just going to completely ignore it. It does not matter. It's not important. We can just forget about it. So that's kind of where I am here. So if we look at one more of these, if I want to consider sketching the graph of the function, I don't know, x squared plus 2 divided by, I'll keep it easy, divided by x. And maybe I'll make this more specific and I'll say sketch the graph. So I need another sticky note here. So I can draw my axes in. Okay, well, let's follow the same procedure we did before. Is there a vertical asymptote? Yes, at x equals 0. So, it's just represented by my y-axis, so I'm just going to draw my dotted lines above and below just as a note for myself. Is there a horizontal asymptote? No, because the degree of my numerator is greater than the degree of my denominator. But there is a slant asymptote because the degree of the numerator is 1 more than the degree of the denominator, right? 2 is 1 more than 1. What you'll notice is that anytime there's a horizontal asymptote, there's not a slant asymptote, and vice versa. So can I find the equation of the slant asymptote? This should say y equals. Of course I can. I can just divide through. If I were to divide through, I'm going to get x plus 2 over x. So here is the equation of my slant asymptote, which I can go ahead and draw it. I think I missed. Let's try this one more time. I can go ahead and draw it in. I need some intercepts. Well, there are definitely not going to be any y-intercepts because my asymptote falls right on the y-axis. It doesn't really look like I have any x-intercepts either. We'll see why in a second. So we've established no y-intercepts. Right, if I were to f of x equal to 0, x squared plus 2 equal to 0 has no real solutions. Well, great, so now what? Well, now we're just going to test a point and see what happens. So when in doubt, you can always fall back on picking points. Right, so I'm going to say, let's just test f of 1 to give myself some direction. I get 3. There it is. Label it. I can test -1. I get -3. There it is. Label it. And what's going to happen here is, just as we saw above, my graph is going to follow the regions given by the asymptotes as best as I can. It's just a sketch, so it doesn't need to be perfect. You just need to be able to show that those are the regions that the graph sits in. So it's still the same process that we're used to doing, with one added step now of just checking for the slant asymptotes.